In this section, we're going to look at doing hypothesis tests, also for means, but when sigma, the population standard deviation, is not known. In the section where sigma is unknown, we're actually assuming a more realistic approach for testing the means of a population. Now, we are going to make some assumptions. Number one, just like before, we're going to assume all samples have an equally likely chance of being selected. That means any sample that would be within the sampling distribution is a possible outcome. We're also going to assume that the population, the underlying population of our data, which we represent with X, is approximately normal. The consequences of this is that if we know that the underlying population from which we are sampling is approximately normal, any sample of any size, doesn't have to be greater than 30, but any sample of any size will produce a sampling distribution, so a distribution of all possible samples of that size, that will be approximately normal as well. And the big difference here is that the population standard deviation, sigma, is not known. And so, in that case, we're forced to estimate the standard deviation of the population with S, which is the standard deviation if it is coming from a sample. So it's the sample standard deviation. This last one is really where the processes that we're going to use and the assumptions we're going to make, this is really what makes this unique to this particular section. So since we are using S, which is the standard deviation, assuming that it came from a sample, when this is the case, we pair up that with the t-curve. And hence, our test statistic value is a t-test statistic value, where we take, just like before, the sample result minus the mu of the population, which is also equal to the mu of the center of the distribution of samples of that size, and then divide it instead of sigma by S over the square root of n. So nothing really changes as far as the formula goes. This is the big difference here. And of course, the t-curve is much different than the z-curve, though as my samples get bigger, the t-curve and the z-curve become almost the same. So since we're using the t-curve rather than the z-curve, we need to use the t-functions on our calculator to find the area, which becomes our p-value. For the area under a t-curve, we use t-CDF rather than norm CDF. We put our lower boundary, we put our upper boundary, just like we do with normal CDF. But the difference here is instead of 0 and 1, we put what the degree of freedom is. This is the most important part because the degree of freedom tells us what type of t-curve we are using. Every time we change our sample size, we get a different t-curve. The lower our degrees of freedom are, so the lower our sample size, remember degree of freedom, you'll recall, is n minus 1, right? So it's directly tied to our sample size. So as my degrees of freedom increase, the tails become closer to the x-axis and are eventually, it morphs into pretty much the standard normal curve, right, the z-curve. But the lower my degrees of freedom, the fatter my tails are, the lower the hump is in the middle, and the more hence my spread out my data is. So degree of freedom is central to the t-curve. Every time we change the sample size, we have a different set, a different t-curve with different areas. And so that becomes one of the more important parts of this. All right, so let's look at a couple of examples here. Let's say we're running a hypothesis test, and in this situation, alpha is 0.05, so that's our significance level. N is 20, and my t-test statistic, I have no TTS there, but our t-value is 1.874, and this is a right-tailed test, meaning the underlying alternative hypothesis has a greater than symbol. If you recall, the alternative hypothesis symbol determines which type of test we have. So we would assume we have a greater than symbol there in my alternative hypothesis. So the challenge here is then find the p-value. I'm just going to draw a quick representation of this. Whoops. So we can visually see it. Visually as we draw it, the t and the z will be the same. And just with z, we have 0 in the center. 1.874 is almost 2 standard deviations to the right. So I'm just going to kind of estimate it here. And then since it's a right-tailed test, the area to the right of that test statistic will be my p-value. Putting this into our calculator, we would put TCDF 1.874 all the way to something really large. And then in this case, we have 19 degrees of freedom. Go ahead and put that into your calculator and see what you get. You may want to hit pause there, but 0.0382 is the p-value, which given our alpha value of 0.05, what would that conclude? Would we reject or fail to reject the null hypothesis? In this case, we would, yes, reject the null hypothesis. And we would say the data supports the underlying alternative hypothesis. And we would put that into words. Let's go to the next one. The next one, we have alpha equaling 10% or 0.10. Consequently, that would be a 90% level of confidence then. My sample size is 49, and my t-test statistic is negative 1.602, and we're going to run a two-tailed test. All right, so I'm going to draw a little picture here so we can visualize this. You see, all my t-curves do not look the same, nor do my z-curves, and that's okay. All right, so we're a little more than 1.5 standard deviations to the left this time. So negative 1.602. And my p-value would be the area to the left of this. We always go toward the more extreme areas. But since it's a two-tailed test, I would also need to find what would be the area to the right. To the right of 1.602. It's important to keep that in mind. Two-tailed tests, and we know it's a two-tailed test if the alternative hypothesis has a not equal to. And that's what tells us a two-tailed test. So in finding this, go ahead and use TCDF to find it. Pause the video. Now, one way we could find this, and keep in mind what we're finding, will be the sum of the two areas. So it'll be this and this. This is what we want to find. And if we do it as 1 minus, so we do it as a complement of what would this, the way I entered it into TCDF here would find the area in between, but then since I'm subtracting that from 1, it actually leaves us with the area that's outside of that. So the two tails already combined together, 0.1157. That means the area inside is 88.8843. But regardless, that doesn't matter. You can also find it on the left, but then just double it because they have the same area. So just multiply it by 2. And in this case, my p-value is greater than 0.10, my significance level. So that leads me to fail to reject the null hypothesis. for our last one. Alpha is equal to 0.01, n is equal to 19, and my t-test statistic is negative 3.015, and it's a left-tailed test. So in this case, we're pretty far to the left. Okay, that was awful. That doesn't even look like a normal curve. Let's try that again. And with 0 at the center, I'm pretty far here to the left, negative 3.015. It's a left-tailed test, so the area behind this, we would assume we had a less than symbol in my alternative hypothesis, and the p-value will be the area over here to the left. So TCDF, go ahead and pause this and see if you can get that p-value. Negative 3.015. Actually, that's my upper boundary. So we want to go negative unbounded, so negative infinity, negative 3.015, and then we have, in this case, 18 degrees of freedom. This gives me 0.0037. So less than 1%, 0.37 or 37/100%, which is less than my significance level of 1%. In this case, we can be confident in rejecting the null hypothesis. There is sufficient evidence to suggest or to support my alternative hypothesis. Of course, we always want to put those into context for our conclusions. All right, let's look at some other examples here, some more realistic sort of story problems here. The deal with these is you want to read them and sometimes read them several times if it is a story problem like this, because we have to identify what our different values are here. For each of these, we do want to pay attention, and in general, as you're reading these, pay attention to this description of the standard deviation. And the context is what is written. So a manufacturer is responsible for making the barrels to store crude oil for the United States, which federal requirements state must hold 42 gallons of oil. As part of a routine quality check, we randomly select 27 barrels off the assembly line and find that their mean capacity is 41.7 gallons with a standard deviation of 0.8 gallons. Can you, as a quality control administrator, say with 99% confidence that the requirements are being met, assume the population's distribution, that's talking about the underlying population from where we're sampling, is approximately normal? I can tell you that the reason why we say that is because of the fact that our sample size is less than 30. If you recall back to the central limit theorem, we're told that the distribution of all possible samples will have a normal distribution for samples of any size, as long as the underlying population from where we're sampling is normal as well. Otherwise, if we don't know what the distribution is of the underlying data, we don't see it becoming normal until we get to sample sizes of 30 or more. So that's why we assume that the underlying population distribution is approximately normal, so we can not be worried about that sample size of 27. All right, I do want to point out here our standard deviation came from the sample of 27. You'll notice it says you randomly select 27 barrels off the assembly line and find their mean capacity is 41.7 gallons with a standard deviation of 0.8. So this is my sample result for the mean. And this number that we calculated, 0.8, came from the same sample of 27 barrels. We had to do that because we weren't told the population standard deviation. So the number 0.8 is based on that sample of 27, which makes that an S value. And whenever we have S, this is when our underlying distribution is best estimated with a t-curve. Okay, so the number that is being disputed in this case is the 42 gallons of oil. Right? The federal requirements state that the barrel size must hold 42 gallons. We want to say with 99% confidence, which this leads us to a 0.01 value for our alpha, our 1% significance level, we want to say that the requirements are being met. So we would have a problem if it was less than that, and we would have a problem if it was more than that. So there's really no direction that they give us. I do not determine the direction based on the result of my sample. So even though 41.7 is less than, that doesn't mean our alternative is less than. You have to look at the wording of the question to determine whether we think, as a researcher, that it might be more or it might be less. Here we would just say not equal to 42. So that makes this a two-tailed test. We'll remember that as we go to find our test statistic. Our test statistic is T because our underlying population underlying standard deviation came from the sample, not the overall population. And the X bar in this case was 41.7. So 41.7 minus 42 divided by my standard deviation, 0.8, over the square root of 27, my sample size. Remember that all of these need to be put into parentheses as you put them into your calculator. Go ahead and see if you can calculate our test statistic. You should get negative 1.949. So my sample fell to the left. Let's keep in mind that at the center here, I'm going to mark what our actual values were. We were checking to see whether the gallon or the barrels held 42 gallons, and I got something to the left of that, less than that. It was 41.7, which is 0.3 gallons less. Now, how far that is less actually is a matter for calculating my T. At the center, T is 0, and so what we find is this is negative 1.949 standard deviations to the left. Now, because this is a two-tailed, I also need to include in my calculation what would be to the right of the positive counterpart of that, positive 1.949. So the area to the extreme values is my p-value here. And as I find those, we're going to go 1 minus TCDF, because we're going to just put in what the area is in the middle, negative 1.949 to positive 1.949 with 26 degrees of freedom. And that will give me my combined area of these two shaded regions. That would be 0.0622. 0.0622. This is my p-value. So about 6.22%. And in comparison to my significance level, alpha, we want to be 99% confident, so my significance level is at 1%. We can see this is greater than 1%, and that does not bode well for the researcher in this case. We would fail to reject the null. Remember that the null is saying that the barrels are equal to 42 gallons. We're failing to reject that, so we're saying there's insufficient evidence to suggest they are not meeting the requirements. In this case, we're saying, yeah, looks like our barrels are good. Our barrels seem to be holding the right amount of oil, which was 41.7 gallons. 42 gallons. Yes, our random sample of 27 barrels had a slightly different average hold, but it wasn't too far off from 42 for us to say, oh, there's a big problem here. So we can say with 99% confidence that the conditions are being met. Let's look at another example. Sarah, a university junior, chose to live on the honors floor of her dorm because she was told that the girls on her floor would be quiet and studious. In fact, Sarah was told the students on the honors floor study 11 hours per week. After living on the honors floor for a few months, Sarah is convinced that the students on her floor study less than 11 hours per week. To test her claim, Sarah polls 10 girls on the floor. Test Sarah's claim, given the results below at a 10% level of significance. Okay, so we've got 10 responses here. That's all we have. So I know my sample size is 10. I know the level of significance, alpha, is 0.10, so 10%. And we know the number in dispute here is 11 hours per week. Our null states that, again, if we just always stick with equals, all we have to do is identify what's the number that's being challenged. In this case, mu is equal to 11 hours, but she's convinced that they study less than 11 hours per week. So she wants to show it's going to be less than 11. Now, some books say your null and your alternative need to be opposites of each other. So if this is less than, it should be greater than or equal to in the null. But we're going to keep it at just equal to. It's best to just say, this is what we think is the center of the universe. And then we'll test to see whether that center might have shifted. Now, we need to figure out what our sample said. And all we're given is the underlying data. So what we need to do is to put this data into our calculators to figure out the two numbers we need. We need the mean of this data set. So what was the average number of hours according to her sample? And we are not given a standard deviation. And so we also need to find S, the standard deviation, the average spread of the sample. So let's put these into our calculators into our lists and then do our one variable crunch on those numbers. You might as well pause it right here and put these on for yourself. So for our sample mean, we should get 9.5. And then the standard deviation of the sample is 2.991. And this now will allow us to find the value of my test statistic, which is a t-test statistic. What we found is that the students fell, indeed, as she suspected, below 11. They fell down at 9.5. So if this is my distribution of means, for the t-values that correspond with those, we would have 0. And now we need to figure out what is the t-value that corresponds to 9.5. So we go 9.5 minus 11 divided by 2.991 over the square root of 10. Parentheses around the top and the bottom. You can skip the top if you hit enter after 9.5 minus 11. You should get negative 1.586. So we're a little more than 1.5 standard deviations to the left. And our p-value since this is a left-tailed test, because of what we see here with our alternative hypothesis, would be the area to the left of that. It's unbounded on the left, so we'll start with negative 1,000 all the way up to negative 1.586, and our degrees of freedom in this case are 9. The area to the left of that is 0.0736. So this is my p-value. My p-value is 0.0736, which, compared to my alpha was at 10%. This is less than that, meaning there is a 7.36% probability of getting this sample result, 9.5, or something less extreme, or something more extreme, so further into the tail, if the null was true. So there's a 7% chance that this result would occur if the true population of the mean was 11. This gives us enough evidence to reject the null. Remember, the null stated that it was 11. We got a random sample that was 1.5 hours off of that to the left. And what this p-value says is, this, if we assume 11 is true, there's a 7% chance that I would see the result I did under those circumstances. So getting a sample of this size with 10 people would only happen 7% of the time. So that's enough for us to reject the null in this case. There is sufficient evidence to suggest that girls study less than 11 hours per week, right? All we're doing here in this part, right, there's sufficient evidence to suggest that's all part of our template that we looked at back in the first introduction of the hypothesis tests. And so here, when we're suggesting that the evidence does support this. So we want to put that into words. So basically, we're just saying that the girls study less than 11 hours per week. Let's look at another example here. A hometown department store has chosen its marketing strategies for many years under the assumption that the average shopper spends about $100 in their store. A newly hired store manager claims that the current average is higher and wants to change their marketing scheme accordingly. A group of 27 shoppers is chosen at random and found to have spent an average of $104.93, with a standard deviation of 907. Assume the original distribution of spending is normal and test the store's manager's claim at a 1% significance level. All right, so the number that's in dispute here is our $100, right? That's being challenged. Status quo is that the average is $100. The marketing person, what do they believe? The store manager, they believe that the current average is higher and wants to change their marketing scheme accordingly. And so, if we're asking to test the manager's claim, he claims that it's greater than 100. And at least at the very outset, it looks like it might have some validity to it. So I just turn that 0 into a 100. The center of the universe is assumed to be 100. If we fall too far outside of that center, we're going to assume that something is shifted, right? In this case, we got 104.97. Now, how far that is all about the standard deviation and the sample size as well are two things that play a role in that. But we know it is more, 104.93. Let's figure out how far to the right we really are. This is the distribution of my samples of size 27. So these numbers represent my X bars. And underneath that, we're going to put our t-values. 0 at the center. What we need to find is here. Now, 27 is my sample size. This is the X bar, the average that they spent, with a standard deviation of 907. So this 907 is an S because it came from that sample of 27. Hence, while I'm using T. So this represents a T distribution. It's a right-tailed test, and so this is what I need to find. Theory to the right, let's determine the test statistic first. Take 104.93, and we're going to subtract 100 from that. Oops, not 1,000. 100, and then we'll divide that by the standard deviation of the sample, which was 907, divided by the square root of the sample size, which was 27. Parentheses, parentheses. And let's see what we got. Plugging this into our calculator, we should get 2.847. So we're almost 3 standard deviations away from the mean. My p-value will be TCDF. We start at 2.847 and we go to 1,000 or something very large. And our degree of freedom here is 26. Plugging and chugging that into our calculators, this yields 0.0043. That 2 rounds up. 0.0043, so that is my p-value. And my alpha in this case was a 1%, so 0.01. This is less than that, and that leads me to reject the null. There's a very small probability that this would happen under the conditions of the null, so we reject it. There is, in this case, sufficient evidence to suggest shoppers spend more than $100 in the store. And so in this case, this gives the store manager the knowledge that, hey, it would be good for us to change up our marketing plan for this situation. This concludes our hypothesis testing for means when sigma is unknown, meaning we have to use S as a substitute for sigma for our standard deviation in our formulas, and then we pair that up with the t curve.